Prime numbers are the building blocks of arithmetic. Every whole number can be broken down into primes, but the primes themselves refuse to follow an obvious pattern. They begin simply enough: 2, 3, 5, 7, 11, 13. Then they keep going forever, sometimes appearing close together and sometimes leaving surprisingly large gaps. Mathematicians can test whether a number is prime, and they can estimate how many primes should appear below a certain size, but the deeper pattern behind their distribution remains mysterious. The Riemann hypothesis is one of the most famous attempts to explain that mystery. It does not predict primes one by one. Instead, it claims that a hidden structure inside a special mathematical function controls how primes are spread across the number line. The story begins with Bernhard Riemann, a German mathematician who, in 1859, published a short paper that changed number theory. Riemann was interested in counting primes, but he approached the problem in a strange and powerful way. Instead of staring directly at prime numbers, he studied a function now called the Riemann zeta function. This function had already appeared in earlier mathematics, but Riemann saw that it could be extended into the world of complex numbers, where it revealed a far deeper structure. His paper suggested that prime numbers are connected to special points where this function becomes zero. That connection turned a question about ordinary whole numbers into one of the most important problems in modern mathematics. To understand why this is unusual, we need to think about what kind of object the zeta function is. A familiar function takes an input and produces an output. But the Riemann zeta function can take complex numbers as inputs. A complex number has a real part and an imaginary part, so instead of sitting on a single number line, it lives on a plane. This gives the function a much richer landscape. Its behavior is not just a curve rising and falling. It is more like a surface with hidden symmetry, special values, and important points scattered through an invisible mathematical map. The Riemann hypothesis is about the exact location of some of those points. The most important points in this story are the zeros of the zeta function. A zero is an input where the function's output equals zero. For simple equations, zeros may be easy to find. For the zeta function, they become a gateway into the structure of prime numbers. Some zeros are already well understood. The zeta function equals 0 at the negative even integers, -2, -4, -6, and so on. These are called the trivial zeros. The name does not mean they are useless, only that their locations are not the central mystery. The real problem concerns another class of zeros, known as the nontrivial zeros. The Riemann hypothesis makes a very precise claim about these nontrivial zeros. It says that every one of them has real part exactly 1/2. In the complex plane, that means they all lie on one vertical line, called the critical line. This is astonishing because the complex plane is vast. A zero could, in principle, appear in many possible places. But Riemann's claim says the important ones are perfectly aligned. Their imaginary parts can vary, climbing higher and higher along the line, but their real part is always fixed at 1/2. The hypothesis is therefore not vague or philosophical. It is a sharp geometric statement about where infinitely many hidden points must be. At first, this may sound like an abstract detail about a complicated function. But the location of these zeros matters because they are tied to the distribution of prime numbers. Mathematicians have formulas that approximate how many primes appear below a given number. These formulas are remarkably good, especially for very large numbers, but they are never perfectly smooth. The actual primes fluctuate around the estimate. The non-trivial zeros of the zeta function help describe those fluctuations. In a simplified picture, each zero contributes a kind of wave to the error between the expected prime count and the real prime count. The placement of the zeros controls how wild those waves can become. If the Riemann hypothesis is true, then the errors in our estimates of prime numbers are as tightly controlled as possible under this framework. The primes would still look irregular. There would still be gaps, clusters, and surprises. But the irregularity would have a deep limit. It would mean that the apparent randomness of primes is not random in an uncontrolled way. It is more like noise produced by a highly structured instrument. The critical line becomes the place where that hidden music is tuned. If even one non-trivial zero were found away from the line, it would mean the prime numbers can deviate from their expected pattern more dramatically than mathematicians believe. This is why the Riemann hypothesis is widely considered one of the most important unsolved problems in pure mathematics. It sits at the center of number theory because prime numbers sit at the center of arithmetic. It was also included in Hilbert's eighth problem, part of David Hilbert's famous list of major mathematical challenges. That same problem area includes other legendary questions, such as Goldbach's conjecture and the twin prime conjecture. Later, the Clay Mathematics Institute named the Riemann hypothesis one of the Millennium Prize problems. A correct proof would earn $1 million, but the real prize would be far greater, a new level of understanding about the architecture of numbers. One reason the problem has resisted proof is that it connects several difficult areas of mathematics at once. It begins with whole numbers and primes, but it must be studied through complex analysis, where functions behave across the complex plane. The zeta function also has deep symmetries and relationships that are not visible from its simplest definition. Mathematicians have developed many tools to approach the problem, and the hypothesis has inspired entire fields of research. But a proof cannot merely show that many zeros are on the critical line. It must explain why every non-trivial zero, infinitely many of them, is forced to be there with no exception. Computers have provided enormous evidence for the hypothesis. Vast numbers of non-trivial zeros have been checked, and the ones tested lie on the critical line exactly as predicted. This is powerful evidence, but in mathematics, evidence and proof are different things. No matter how many zeros are verified, there are always infinitely many more beyond the range of computation. The next trillion could behave perfectly, and the question would still remain open. A single zero off the critical line would disprove the hypothesis. That is the unforgiving standard of mathematics. A statement about infinity requires a proof that covers infinity, not just a very large collection of examples. The hypothesis also has relatives in other mathematical settings. Some analogues of the Riemann hypothesis have been proved, including important cases involving curves over finite fields, where André Weil achieved a major breakthrough. These results matter because they show that the basic idea can be true in related worlds. They suggest that zeros lining up in a special way is not just a numerical accident. However, those successes do not automatically solve the original Riemann hypothesis. They are clues from neighboring landscapes. They provide inspiration, methods, and confidence, but the classical zeta function remains its own mountain, and the summit has not yet been reached. So the Riemann hypothesis remains suspended between overwhelming evidence and missing certainty. Most mathematicians expect it to be true, but expectation is not enough. If it is proved, it will confirm that the prime numbers obey a remarkably precise hidden law. If it is disproved, the shock would be enormous, because it would reveal that primes are wilder than the dominant theory suggests. Either outcome would reshape mathematics. At its core, the hypothesis asks a simple question: do all the non-trivial zeros of the zeta function lie on the critical line? Behind that question is something much bigger: whether the chaos of the primes is secretly balanced by one of the deepest patterns in mathematics. If you found this helpful, please like this video and subscribe for more explainers.